In example 6 and 7, we want to solve each of the following separable differential equations. And these are some review problems that don't necessarily utilize exactly this particular lesson, but definitely will utilize our knowledge of solving for a particular solution with these ones. The very first thing to do here is to separate our variables. So we're going to multiply each side by dx, and the dx's here will cancel. We'll be left with dy is equal to 5x to the fourth cosine y cotangent of y dx. And then we're going to divide each side by cosine y cotangent y. We want to get those y's over to the other side. And that's the first step, is to separate your variables. So the cosine's gone on the right, cotangent's gone, and then actually what we're going to do is we're going to represent the left-hand side with the reciprocals of the cosine and the cotangent. So the reciprocal of the cosine is the secant, and the reciprocal of the cotangent is the tangent. Still have dy, and that's going to be equal to 5x to the fourth dx. Once you've separated your variables, you'll now take the integral of each side, and we'll need to find the antiderivative of each side here. So recall your derivatives, and the derivative of the secant is actually secant times tangent. So the antiderivative of secant times tangent must be the secant. On the right-hand side, we need to add 1 to the 4, that's right here, and then divide by the new exponent. So we'll wind up with x to the fifth. And if you take the derivative of x to the fifth, you get right back to the integrand 5x to the fourth. Of course, we need a plus c. To solve for c here, what we'll do is we'll substitute our initial condition, which was 0, 0, into both x and y here, I guess, 0 for each one. So 0 to the fifth is 0. We need to figure out what the secant of 0 is, which is the same as 1 over the cosine of 0. So the cosine of 0 is 1, and 1 over 1 is 1, making c equal to 1. So then we'll take this line right here, where we have the secant of y equal to x to the fifth, then that'll be plus 1. We just found that value of c. And the last thing to do here is to just solve for y. So y will be the inverse secant of x to the fifth plus 1. Moving on to the last example, here we have dy dx being equal to negative 2x sine squared y. We'll multiply each side by dx, and we can also divide by sine squared on each side. So the dx's cancel, the sine squared y's will cancel, and 1 over sine squared is the same as the cosecant squared using your reciprocal relationships. The dy is still there, that's good. And then we've got a negative 2x dx left on the right-hand side. So we've successfully separated our variables, and what we want to do now is take the integral. It's not a very good integral symbol. Take the integral of each side, and we'll find the antiderivative. Remember that the antiderivative of the cosecant squared is the cotangent. So the derivative of the cotangent is the cosecant squared. So our antiderivative here will be the cotangent of y. Now that's going to be equal to the antiderivative of everything on the right-hand side, which happens to be negative x squared. In other words, the derivative of negative x squared is negative 2x. So that's a good thing to do when you're wondering if you found the correct antiderivative. Of course, we need the plus c on the right-hand side. Our initial condition is right here. Y at 0 is 4. So we'll have the cotangent of 4 being equal to negative 0 squared plus c. So c will be just the cotangent of 4. We can't actually figure that out. It's not 4 pi, so we're just going to leave it as the cotangent of 4. And we're going to go right back to the line when we found the antiderivative, and that was the cotangent of y is equal to negative x squared plus now c here we found to be the cotangent of 4. And to solve for y, which is an angle, we need to use the inverse cotangent. And it'll be the inverse cotangent of everything on the right-hand side.